Okay, so here we go. Thanks for joining again. So yeah, today we're gonna continue the project DiSco MIMO, where I sort of reproduce my grad school paper. And this is the block diagram. Okay, so we have the paper, which is this paper here, just as a recap, but it'll be in the link of the video. But we want to do this from scratch, and we already, in the previous episodes, we set up a Git repo with UV pipe project, some pre-commit hooks. We don't have typing yet, but we do have a bit of PyTorch and signal processing. Well, today I want to get right into it. One big thing we'll do today in this episode is let's add the diffusers dependency and let's instantiate our first deep neural network, okay, for a diffusion model. So we'll take a look at diffusers, and we're going to use an architecture called UNet. And I think it's good to do a diagram. So we had the matrix multiplication we did last time. But long story short, the big idea behind a deep, okay, so we have let's call it a deep neural network. Well, which is actually a diffusion model, right? So a diffusion model, when we say a model, it means it's a so-called deep neural network. And generally speaking, in the broadest case, it only has two properties when you view it from the outside, okay? So it takes as input two things and it outputs one thing. And the two things are, one of them is a tensor of shape S. Okay, so tensor means either a scalar, a vector, matrix, 3D, matrix, etc. Right? It can be 4D too. But the key property of a diffusion model, okay, then the other thing it takes is a scalar, t, which is called the time step. And it outputs a tensor of shape S. So this is the key property, right? It has two inputs and one output, and the shape of the output is equal to the shape of the tensor input. It's also a tensor of exactly that same shape, okay? So that's all we need. We can do any deep neural network in the world. We can use any deep neural network that has this property. The most common class is a UNet, or more modernly, let's call it a VIT, vision transformer, or even a specialization of it called DIT, diffusion transformer, which is really just a VIT, but, well, actually, let's just do a DIT then, right? So it's either a UNet or a diffusion transformer. Common, modern, right? So there is an archaic name for this, is an autoencoder. Like, it's almost an autoencoder, right? Because it takes as input a thing and outputs this something else of the same shape, except there's this tiny little scalar t. This can be either integer or float, okay? And we're gonna work with integer, so let's just leave it integer t. Okay, and that's it. This is the crash course in a diffusion model. So we can write the diffusion model from scratch in PyTorch, but that's probably a bit too much for today. Instead, we'll just go the Python way and we'll install the diffusers package, and we'll look at the docs and we'll instantiate the most basic UNet. Now let's talk a bit about the shapes here, right? So again, we said that this thing is an input, right, of some shape. Let's say it's a rectangular 2D matrix, then this thing will be exactly the same shape, but different contents, okay? So it's not supposed to copy the value. So this autoencoder like is a bit, maybe it's a bit disinformative, because we don't really want the diffusion model to just copy the values. These values will be different, but the shape will be exactly the same, okay? And we have some examples of, let's see, what are scalar, it's the temperature, for example. So you can train a diffusion model that it will be a generative model for generating the temperature in somewhere according to some distribution. Vector, this is audio, right? So an audio signal is usually a single channel, or let's put it single channel audio, right? That's usually just a vector, right? Matrix. This is a grayscale image, not just an image. It's not enough to say image, it's actually a grayscale image. 3D matrix. Which is usually matrix plus channels, channel dimension, okay? So these are RGB images, because this is a pretty common misconception. When you represent what we call a regular image in numbers, it's not a 2D matrix, it's a 3D matrix, because it has a dimension of 3 and then the height and width. This is also wireless channels. Why is it not a matrix? Because these are complex valued, so they have a real part and an imaginary part. But there's other examples here for what else is a real 3D. There's also 3D matrix that's not so it's 2D data plus channel dimensions, but there's also raw 3D data matrices, which we can imagine. For example, a grayscale video, okay? And then a 4D matrix, it can be 3D data plus channel. This is what you would call a video, okay? So everything here, including stuff you see like in Sora or whatever other popular generative models are today, they all pretty much use diffusion transformers, which are, they follow, they're just a deep neural network with this property that the input is the same shape as the output and it's just different shapes. So we're gonna work with a 2D unit with channel dimensions, right, from diffusers. And that's it. That should be enough. Let's get to it then. Okay, so we have our project here and we are on the main branch, and we're gonna check out the branch diffusers off of main, and that's it. We're on that branch now. So what do we want to do? We need to add diffusers first of all as a dependency, okay? So let's take a look at diffusers. Hugging face. This is what we're gonna okay, their installation is old, but we need to add UV add diffusers torch. Let's take a look at GitHub. Oh, where do they keep their dependencies? Oh, they have the setup PY version. Okay, so this is very old. Okay, so let's then, in any case, we don't care because UV takes care of everything. So let's add UV add diffusers torch. Let's see what it does. Is it gonna pull PyTorch for us? No, we already have PyTorch in the environment. That's good. It adds a bunch of dependencies. And then install diffuser 0360. So I like to pin it down, 0360. Okay, that's it. And we're done. So we can add the dependency and commit it. That's how easy UV makes it. Add dependency. Now our pre-commit hook is gonna kick in. Okay, everything is good. And we can create the new branch upstream. And that's it. Okay, the other thing is we have to use it, right? So we have to think about how we structure our project a bit, because we want to keep this clean coding. So, interestingly, we don't really need a models file now, because we're not going to define any neural networks in this project. We're just going to import them. But let's do it. Let's do a models file, models.py. Okay? And we just want to say what? Import. Well, let's just import directly from diffusers. Import, it's called UNet 2D model. That's it. Here it is. Let's take a look at it a bit. Yeah, so it's a 2D unit model that takes a noisy sample and the time step and returns a sample shaped output. This is exactly what we talked about, right? So let's ignore what noisy means for now, but it takes as input a sample and a time step, which is a scalar, and returns a sample shaped output. So 2 inputs, 1 output. Now to get a better clarity here, we can look at the forward method. So the sample is a tensor and the time step is the union. It's either a float, an integer, or you can already feed it a tensor. And to make something simple, we're just not even going to use the time step. We're going to set it to a constant for everything. But we'll explain that when we train the model. But for now, let's learn how to use this, let's say, uninitialized model. Because you can use a deep neural network even without training it. It's going to be gibberish. We won't know what the output represents, or it doesn't represent anything. We're not going to be able to use it in any application. But at least we'll know the code is running, right? We can pass through a neural network on GPU, which is not a small thing. We can already, for example, so let's configure the shape of the network, or let's figure out what parameters we want to expose to users. Remember, in the grad school project code we also looked at on this channel, in the sort of the other pre-series to this, we were not happy because there were too many parameters the user had to set at the application level. So what does it have? Parameters of the init method. Sample size. This is critical, right? Because it's the shape, it's a 2D shape. And the third dimension is the number of channels, right? Input, output. These are going to be equal, and for wireless, they're always 2. So we want to configure the sample size, and the only constraint is that it must be a multiple of 2 to the power of the number of blocks minus 1. So let's try to draw a bit how a UNet works on the inside then. Okay, so now we're gonna go inside this box, okay? What it does is, it takes as input the data. I'm gonna ignore the T. And it has things called blocks, okay? So this is a block 1. This is block 2. This is block 3. And it has down path blocks and up path blocks, and their numbers, the number of down and up path blocks, are equal. I'll explain what that means. We'll crash course into what that means. So if I put 3 of these down path blocks, or let's actually draw them like they draw them in the paper, like this. Okay, so I have 3 of these. I need 3 up path blocks, which look kind of like this. Okay, so down path and up path. We know the output is the same shape, okay, ultimately. So what happens to the signal in between, or the matrix or image in this case, right? What happens is, after every block, okay, let's color these differently because these are down blocks, sorry. So the down blocks will be green. Okay. What happens is the signal flows like this. Okay, so we take our original image, it goes into the first down block, and it comes out smaller in both shapes. Okay, so if generally by a factor of 2, so then this is going to be half on this shape and half on this shape, which is considerably tiny. Okay, then it goes again. After the second down block, it's going to be even tinier. It'll be half on this shape and half on this shape. Okay, again, after the down block 3, which is the deepest block, this is going to be the smallest image ever, but this is how it works. It goes like this, and then it starts to, after each up block, guess what? It becomes larger again, okay? Until, of course, it comes out by the same factor. So it increases by the same factor until it comes out having the same shape as the input had. So let's see, let's color these differently now. Maybe with the gray, right? And the only other thing the UNet does is, which was really the breakthrough at the time, is that these up blocks are a bit different than the down blocks, because they actually, let's color these different too, the ones on the up path. Let's see, something like purple. Now there's one difference in the UNet, which kind of was a breakthrough at the time, but very old, in 2015. Look at the shapes, right? What else could this up block take as input? Because it takes as input this guy and outputs this guy, but we have another thing of this shape right here. So then the UNet uses what are called skip connections, where this signal also gets seen by this block. Okay, so let's try to draw this something like, well, I guess it is a straight line, right? There's really, so yeah, so this signal gets seen by this block too. Actually, we can make this, probably lift it up a bit. There we go. Okay, so now we have the down path here, but also we have this signal replicated here. And what happens is, I don't remember what actually happens. There's a few options to combine them. The simplest, you can just do a sum, right? Or you can glue them together in sort of a signal that's 2 times wider just on one size. But in any case, the point is that it has these called skip connections. So it has another one too. These kind of look like a ResNet, which is even older. But they're also more shape controlled, okay? So this is a UNet, right? So this is now down block 1, down block 2, and down block 3. The down stands for down sampling, okay? So this is, and the input is our tensor input, and this is the tensor output. Okay, and what do we have here? I guess usually it's common to count the up blocks in reverse, so they're paired, right? So this would be up block 3, which is the twin of down block 3, up block 2, which is the twin of down block 2, and finally up block 1. Now the number of blocks, now you understand why. Finally we can go back to the actual diffusers code, and now we get why. So this is a UNet, right? And we're done. This is a UNet. Or let's say with 3D, 2D data plus channels input. Okay, so there's also a channel size, which I'm not showing here, because remember, an image or a wireless channel in our case, it's not really a 2D signal, it's a 3D signal, because it's 2D plus the channel dimension. Okay, but that's fine. And so this is basically a UNet. Now, of course, if you know a bit about deep learning, inside of each blocks, there's the so-called weights, right? So, and by the way, one of these things, actually, this is good to expand even further. So let's see, let's do it like this. Let's move this here. because this is the expansion of the, do I have a thing here, like sort of a, okay, so this architecture expands into this, and now each of these blocks also has layers inside of it, okay? Let's see, we have to use something else for a layer. Let's use a dark green or something with a solid background, I guess. Oh yeah, like this, okay? Or a gray. So this down block itself, now remember, this down block will take as input something like this and must output something like this. So it'll have a convolutional layer, okay? And it'll have activation function. This is pretty common in deep learning, right? Layers and activations. And it also has spatial pooling. Only the last time, right? So this is how you get, okay, so then this is inside each block. And then of course each block, whoops, I guess these spaces are way too tight here. Yeah, this is not gonna work. But anyways, you get the point. Let's not spend too much time on this. Okay, so this collection of things would be sort of how a block, what a block could expand. So now, you know, deep neural networks also have, I mean, layers also have depth, right? So maybe you want more layers. Well, you just do something like this. You have now each block has 2 convolutional layers, followed by an activation, and then you finally do the spatial pooling. This is the only operation that changes the size, right? Changes size to get the right output. And I don't think you can go even lower. This is the lowest level you can pretty much go in deep learning. Like, you have enough now. We could implement all this from scratch, but that's going to be a lot of effort, so we're not going to do that. Instead, we're just using the Hugging Face diffusers. And let's look a bit at the code just to confirm that everything we said is right. So we have the UNet 2D model. It has the sample size, which is the input. It has channels. Now we understand, again, it has you can specify the number of channels after each block. So if I see this default, this tells me that this is, by default, this UNet will have 4 blocks. Okay, so that means each dimension must be divisible by at least 8. Okay, because I think another thing is the first block in this implementation does not change the size. But in any case, they could have not put -1 here, so it would have had to be divisible by 16. Then you can choose the down block types and the up block types. There's also a mid block type, which, as you can guess, you can easily guess what that is now if you look at this drawing. It's something between, it's more layers in these skip connections, right? Because you can just put layers here too. So an even more complete drawing would be, let's do it then. We can have also mid blocks. Okay, so this would be mid block 1. And then we have what we talked about. This goes here. Now this mid block must preserve the shape, right? Because the up block has to see the same output as the down block. And then so on and so forth. We can have a function here that says get model. Okay, and it has a config, which is a UNet config for now. Okay, and what do we need to do? It's model equals UNet 2D model. We just need to initialize this. Okay, so we have sample size equals config.sample size. Now remember, in channels 2, this will be hard coded for us. There's rarely any reason, maybe there is, maybe there isn't, but for now we're gonna get this at 2. We're gonna set this to 2. And the other two things, we need our block out channels, which we take from our config, and layers per block, config layers per block. Okay, let's not do the missing thing. Maybe we'll skip omega comp. So let's say the default shape is 64, 64. Okay, so then that's it. Then we can return the model. So then this is a function that takes as input a config and returns a UNet 2D model instance. And then we can write the small main for this Python submodule. Okay. Let's actually write a blank main. So then we can say config equals UNet config. Okay. And then we can get the model, get model with config. Okay, so what do we need to do then to validate if this works? Well, we need to generate some data to put in, right? So we can say generate random input data. Now, remember that, actually I am gonna need the num channels because it is more convenient, right? So num channels is 2, which is an integer. And we'll just say this is config num channels. The reason why I want it here is because it makes it easier for us to generate random data. So we can say x equals. Now what do we know? So it has to be 3D data, right? And actually because of how PyTorch works, it's actually it always has a first batch dimension too. So it's actually, we went all the way to 4D data now, but this batch doesn't count in the diagram we did earlier, right? So a batch of videos would be 5D then, right? Because you would have batch, time, channels, height, and width. Okay, so then all we need to do is we need to set the batch size. We'll just set it to 1, okay? And that's it. Then we can do torch random. Okay, so we need to import torch. Okay, so now we can generate random data of batch size. The channels we have, they're config num channels. And then we also have config sample size, which we can unravel like this. So these are actually 2 values here. So now we can just run this uv run-m mimo.models. That's it. Let's see. Well, it's gonna take a while because, well, not really, because it'll try to load it on GPU. We should have added a few more status prints, but it's fine. We're gonna have to set up logging too. I believe it's still trying to load it to... Oh, okay, it actually made it. Okay, nice. Good. So actually, we were able to run inference. The model has... It's a big one. It has 274 million... Yeah, so this is what you would call it's a 274 million parameter model. And let's see, what data did we put in? So x.shape, 1, 2, 64, 64. What is the size of the output? Well, we know from units it should be the same. Sorry. So I forgot, this has return dicts. So let's see, type, what is the return? Okay, so what does it have? Keys? Okay. Okay, so then we can say y sample dot shape, okay, because it returns a dictionary. It is the same shape as the input, but this should not be the same. Equal x. Yeah, it's not, right? So then, okay, good. So then everything works, because we can also look at some random data. Like if we look at a slice of data in the first channel from 10 to 14, 10 to 14, this is some data. And then we can look at this in the input. Clearly not the same. Okay, so everything works. So we were able to pass a signal through a deep neural network and actually with a trainable model. We forgot, we should have done with torch inference mode. Okay, and we can do outputs, and y is outputs sample. Okay, the only problem is this code will, I guess we can do some print here, right? Input shape is x.shape, output shape is y.shape, and that's it. Now the only problem is this model is still very large, so we have to shrink this. Yeah, we have to shrink these channels. So let's start with something more human. Like what do they do here? Do they double, triple, quad? Right, 224 times 4, yes. Okay, so we'll start with 16, 32, 48, 64. This should be a much smaller model now, so we can run the same code again. Okay, no more breakpoints, everything is good. We can actually add this now. Git add. And let's make this 16, so then we can say here norm num groups 16. I don't know if it's a good idea. Actually, this is good because I've never played around with this in oh, sorry, not 16. I meant to say config dot this. Okay. Okay, now this ran a lot faster now because the model is way smaller. It only has 1 million weights, and that's it. It runs a lot faster. It preserves the input-output shape. Let's test it on other shapes. It should still work. Because it has 4 blocks, the shapes have to be divisible by 2 to the 4 minus 1, which is 8, 2 to the 3. So we can also try a 1664 shape. This should run the same way. Yeah, okay. So that's it. We're able to use a diffusion model. Now we still don't know what this time step, I meant the UNet model. But then we're very close. Now that we have this, we can actually write the training loss and we can train this model to do certain things. So yeah, that's a good thing to do after, well, for YouTube in the next episode.